You are here for optimizing ELB traffic for high availability. I'm John Zobrist. I lead customer success at Elastic Load Balancing, and with me is Enrico Liguori, who is a solutions architect. Today, we're going to talk about some different things you can do for your applications that we deliver over the internet for high availability, and deep dive into the routing we have on the load balancers themselves, as well as a dive into a new feature we just launched that wasn't announced before, but just before reInvent, the LCU capacity reservation, which we launched for application and classic load balancers. So kind of a bonus item there. After the session, you should have a better idea of what high availability looks like in AWS, how you can configure your load balancers and other systems to ensure that your traffic is being routed to healthy and adequately scaled endpoints. You'll know about DNS. We like to always talk about DNS. And you'll know how some of the advanced routing features of application load balancer can be used and some best practices. And of course, we'll cover the LB capacity reservation. We use a few different icons during the slides to indicate we've got internal details, or if there's a new feature launch, or links to documentation for a QR code. We'll pause, try to give you time to take pictures of that. The recording will be on YouTube afterwards, so we do have a lot of content to get into. So let's jump right in. We're all here because we deliver applications over the internet. Now, when I say internet, it could be the public internet, it could be private networking. Generally, these days, everybody's landed on IP networking. We do use two protocol versions today, 4 and 6. One of the nice things about a load balancer or a bunch of AWS systems is you don't have to learn and ramp up to IPv6 across your entire stack to get the benefit at the front door. We're also going to be talking about TCP and UDP, and then on top of TCP, HTTP request traffic, and we'll talk about the different load balancers and how they route for the different protocols. For our example here, we've got just a normal client, so how do your clients connect to your services? And just very, very generically, a lot of you probably already know this really well, but just so we're all on the same page, your client's going to have a network. They're going to get some kind of gateway. With IPv4, they're going to have private networks, and then the gateway is going to NAT them to a public IP where they can then connect to the rest of the internet. If your application's in AWS, this eventually ends up at an ingress gateway, which usually does the opposite kind of network address translation, sending the traffic to your private network. One other thing we're going to do, so in all Elastic load balancers, you've got Route 53 built in with health checks and DNS. So when you create a load balancer, we create a host name that's unique, and you can use that for CNAME or a Route 53 alias, and your clients will connect to that and then get into the traffic to the load balancer. We use this for everything, so we do this for health checks, we do this for adequate scale. If you look at DNS for your load balancer, those IPs will be the ones that are adequately scaled for the detected level of traffic, as well as healthy and passing health checks. Now, CloudFront and Global Accelerator are both great things to put in front of your load balancer, and all of these three systems give you roughly the same options as far as what you can do for availability, but some of them, like CloudFront or Global Accelerator, have some additional features you can leverage. For this example, or for my part of the talk, we're going to focus on Global Accelerator, the main benefit of which is to get your clients onto the AWS backbone as quickly as possible. They've got a great demo on the product page that goes through and can run a whole test. You can see the actual difference. And the benefit here is you get to one of the many edge locations where we have private capacity that we then route to all the regions. So in a simple setup for one zone or one region, your clients would connect to the closest edge location, and then from there, it would be AWS backbone all the way to the closest region that your applications are in. We have the option to do this to many different regions at the same time, and this slide is highlighting that you've got the health checks for each of those regions are something that we're doing at multiple levels, and just like Route 53 takes an IP out of DNS when it goes unhealthy, AWS Global Accelerator will send traffic only to the healthy IPs. And generally, when we're saying traffic, we're talking new TCP connections if you're doing TCP or UDP, and HTTP new requests if you're doing HTTP. So if we zoom in to a single region, we've got under the hood our ALB FQDN, and you can look at that and you'll see usually one IP address per zone, but an ALB can scale to multiple IPs per zone depending on how big it grows. Each of those IPs is independently health checked by Route 53, individually a target from Global Accelerator that it can be routed to, and able to be failed out of DNS if it becomes unhealthy. So one of the things that a lot of people have confusion about that we'd like to get rid of the confusion for is when are you going to fail out of an IP or a zone? So when you look at your load balancer and you see that you have all these different IPs, how do you know which ones are healthy? Or what should you expect if one of them becomes unhealthy? These are the different reasons that a load balancer IP can fail out of a zone. Now, a network load balancer is slightly different than an application load balancer because it'll have one IP per availability zone, and that IP won't change for the life of the load balancer. So when you create it, if you're using a public load balancer, we recommend using a public EIP that you pre-allocate because you get to keep that. Or if you just allocate an internal or an NLB without an EIP, we'll use one. We'll just pick one from your range. And when we're looking at that, when you've now got your individual zone, so on network load balancer, a zone can be failed out of entirely by just pulling that one IP. On ALB, you could have many nodes in that zone, and so part of the zone could be healthy and part could be unhealthy. The other thing that can trigger these, so the target group that you have on each of your load balancers can fail your health check, and I went deeper into this last year if you want to go back and see kind of a deeper dive into this feature. It does let you change the threshold. So today the threshold is 100% unhealthy for everyone. That's the default. AWS doesn't like to change defaults on people, so we didn't change it when we brought this feature in. We recommend people look at it and see what makes sense for you and configure it. This does two things. There's two settings you can set. One is the target groups fail open, and remember, fail open means treat all targets as if they were healthy. So if you have the default, 100% of your targets need to be unhealthy to trigger fail open. The more relevant part of this is the next setting, which is to fail DNS. So you can set both of these settings, and you can set it in a way that effectively disables the Route 53 health check. Maybe you have a target group that you're populating. It's not expected to be healthy. Flip this to you don't want it to ever fail the Route 53 health check. But if you have a case where maybe if half of your application in a zone is unhealthy, you want to actually fail out of that zone, this setting would do that, and it would propagate forward to anything in front of that that's also using Route 53. So the other big thing that you can use here is the arc zonal shift. All load balancers are integrated with it. With zonal shift, you can say, this zone is unhealthy, we want to fail away from it. And we just launched, or they just launched, auto shift, which lets you say, if this zone is breaching these dimensions on these unhealthy characteristics, fail out of the zone. And that you can turn on, and it's automatic, and it's completely under your control what to say should fail and what to say won't fail. For ELB, we will sometimes shift out of a zone. If there's a big issue, we might fail all load balancers out of that zone. We do try to take precautions to minimize impact when that happens, if someone has, say, a healthy zone and all of the other zones are unhealthy. But there are risks there that you should go look at and say, the best practice is use every zone on your load balancer that's configured. So if you have a zone that you're not actually using, don't leave it configured on your load balancer. Create a new one without it or remove it if it's ALB. So those are the first few things. We talked about the target group. There is one exception to the target group, and that's the NLB empty target group. So on ALB, the default is cross-zone is on. So we think an empty target group is less of a risk, and it has a blast radius to fail everything out. But on NLB, the default is the cross-zone off. Because of that, an empty target group, we defaulted to say that counts as unhealthy. Now, you can disable it, but if you have empty target groups in some zones and cross-zone off, you could have a case where you have zones that they're not in DNS, and if something triggered that zone that was healthy to fail out of DNS, you would now be failing open and potentially sending traffic to unhealthy zones. So populate zones that are filled, use ARC and configure auto shift when you're ready to shift traffic out based on application or whatever metrics you want to select for that. When this fails out, whatever IPs are detecting the failure in the ELB will be removed from DNS. And that happens automatically. You can change the thresholds, or you can do it manually with auto shift. So if we go back to our global application and we pivot our view to look at the targets that you have. So these are application servers in a bunch of zones and spread out through 6 regions in the world. We're using Global Accelerator. We have it locating the traffic to the same geo proximity for any of the regions that are there. If we zoom in on this, we can see that each of these regions will have at least one IP per zone on the ELB. Those IPs are all health checked by Route 53, as I mentioned. And if those health checks fail, we'll pull those out of the zones. So if we go back to one of the regions and we just look and say, okay, each of these IPs relates to a machine in a single zone. And if one of them becomes unhealthy for whatever reason on the previous slide, that gets removed from DNS. If we zoom out to a global perspective, we can see that you can have a global application that's actively routing around multiple zonal failures and possibly even regional failures. And with that, when you send traffic through Global Accelerator, you'll get routed around any of the unhealthy zones and routed only to the healthy zones. Now, one other side of this that we do is the same health check that Route 53 is doing, we're doing on the node itself. So when we ping the node and say, are you healthy? Route 53 is doing the exact same thing. Their action is to remove it from DNS, and our action is to actually go replace it. So we'll detect it as failed. We will pull it out of DNS, but that is not as fast usually as Route 53, which takes about 30 seconds to trigger, and the DNS TTL of 60 seconds, so about 90 seconds, and you get IPs completely out of DNS. Client should be reconnecting if they have any errors, and then we'll come in and replace the node if the same failure occurred. We have another system that we're actually looking at that the node's performance across its peers. So we take all of the nodes in a load balancer and say, which one of you has any outlying metrics? And if it's a metric that means you're having a problem, like maybe higher ELB 5XX or higher unhealthy host count, then we'll proactively and gracefully remove that IP from DNS and add a new node to replace it. And then we'll come back later and do some checks and say, was that a good replacement? And we do this anomaly detection on every load balancer, every 5 and 15 and 4-hour window of every day, all the time. And this is detecting failures that are gray failures that aren't enough to trigger the health check. And again, this is on the AWS side and not on your target group side. So on NLB, we have a similar thing. That was ALB. On NLB, we have something that we tag onto the health check packets. So we're using AWS Hyperplane under the hood, and AWS Hyperplane gives us an ENI that is like an Anycast IP address that is integrated with EC2 software-defined networking. And what that does is it can distribute traffic coming in amongst a host of resources that are supporting that traffic, and then they'll route it to the target. We can change all of those under the hood without affecting the in-flight traffic because of that integration with Hyperplane. But every health check goes through that same path. So when you create your NLB, we have an ENI. When we send the health check, we send it through the ENI to the targets. And if we detect that it was dropped somewhere along the way, we can proactively shift that load balancer as a gray failure out of that zone. So you might see sometimes where that IP for one zone got pulled out of DNS, and if you don't see any problem with any of your hosts, then it could have been this case where we're actually proactively shifting out of it. So last year we talked about how we integrated with zonal shift for the application recovery controller. This lets you proactively decide, I want to shift out of this zone based on whatever you want. We did make a change this year, so we now support cross-zone on with zonal shift. In the past, you had to have cross-zone off or zonal shift wouldn't work, and now you can actually have it on. When we shift out, we currently will shift out the whole zone. So we'll shift out the entire IP, and traffic shouldn't go there anymore, even if cross-zone is on. I mentioned a little bit the auto shift, which is a new feature that Arc launched this year, and it lets you configure alarms to say, if these are breaching, fail out of the zone. And a reminder that this is in addition to all of the other reasons that will fail out. So to recap, we have zones that we will fail out of logically. These are our EC2 blast radiuses, where we say everything in this zone has no relation to everything in this zone. We try not to cross anything over. That means things like earthquake places or floodplains or power grids. We keep those separate through all of the zones. And we have many things that can trigger an actual zonal failover, including ones you can't control. And with that, I'll take a break and hand it over to Enrico.
Thank you, John. Now, how the traffic distribution to targets in ELB is actually a result of multiple decisions taken at different levels. First level of decision is regarding the ELB IP selected by the client in order to send traffic to the load balancer. Once this traffic arrives to the ELB, a target group is selected by the ELB to handle the traffic. The third phase is regarding the actual target selection within the selected target group. Now let's review each one of these phases, starting with the ELB IP selection. The selection of the ELB IP used to send traffic, it is made by the client and it relies on DNS. In fact, when a customer creates a load balancer, an ELB, a DNS name is going to be generated and assigned to the load balancer. This DNS name will return the IP addresses assigned to the ELB, and the number of these IP can change depending on the product used. With network load balancer, there is an IP assigned for each availability at zone, and with application load balancer, there are always at least 2 IPs assigned, and then this number can grow up to 100 IPs. Regardless of the specific type of product, the right way to access an ELB is through this DNS name. So the first thing that is going to happen inside a client is the DNS resolution. The client sends a DNS query to rooftt3, and for what John shared before, rooftt3 is the AWS service maintaining a list, an updated list of healthy IPs assigned to a load balancer. And those IPs are also the ones that are considered scared enough for the detected workload. So rooftt3 is going to return the list to the client is going to select one IP in the list, and usually it is the first one in this list. This is also why ELB, while returning DNS queries for the same DNS name to multiple clients, is always trying to return them in a different order. And this is done in order to influence a more balanced decision across all the IPs available. Now, ultimately, it will be still a client decision, the one regarding the IP used to send traffic. So for this reason, it is extremely important that customers configure their clients in order to resolve the DNS when they want to send traffic to an ELB, and also to respect the time to live associated with the DNS entry. This is important with application load balancer because we know that IPs are dynamically changing over time, but it's important also with network load balancer because, as John shared before, there are events in which NLB control plane can remove an IP from the DNS name. So when customers configure their clients, they should always take in mind the fault tolerance and high availability aspect of it. In this example, it means configuring those clients to refresh the DNS when a TCP connection is closed unexpectedly. And this is done in order to allow the clients to get an updated list of healthy ELB IPs. Then when reconnecting, clients should use exponential backoff and jitter. And this is done in order to overwhelm a specific ELB IP in case a large number of clients are reconnecting all at the same time. Then it is a good idea to try another IP address in the list in case a client is experiencing problem with a specific IP. And this because even if it's true that the ELB control plane has systems to detect when an IP is unhealthy and replace it automatically, it's also true that this process takes time, usually about 30 seconds. So in order to expedite the recovery process of a client, it is a good idea to try other IP addresses in the list. Now, this selection of the IP made by the clients, it might have a direct impact on the traffic distribution produced by the ELB. This is true when the cross zone is disabled. The cross zone is a setting that allows the ELB to send traffic to targets that are located on a different availability zone compared to the IP that received the traffic. So when the cross zone is off, it means that the ELB is going to select only the targets that are within the same availability zone of the ELB IP that received the traffic. This means that if the clients are not selecting in a balanced way all the IPs available and the cross zone is off, then this will result in an uneven distribution. As it is showed in these slides, here we are seeing a graph showing the number of requests received by some targets. So I perform a test with 4 targets in a target group, 2 in each availability zone. And as is it visible, essentially only 2 targets were receiving traffic. And this because my clients were sending traffic only to one ELB IP, and the cross zone was disabled. When customers detect this kind of uneven distribution, they should consider to enable the cross-zone setting. And this will allow the ELB to consider all the targets in the target groups when making a selection on which target should receive the traffic. However, they should also be aware that this might increase the charges applied to the ELB. And this is true with network load balancer, where when a request is crossing the boundary of an availability zone, then an inter-AZ charge is going to be applied. However, this traffic is free of charge in application load balancer. Now, let's move to the second level of decision, and this is regarding the target group selection. I'm going to focus only on application load balancer, because with the other products, network load balancer and gateway load balancer, the selection of the target group is actually fixed based on the listener that receives the traffic. This because customers can only configure one target group behind a single listener. While with application load balancer, this is not true. Customers can configure multiple target groups behind the same listener rule, behind the same listener, and then they can leverage for these listener rules. This means when an HTTP request arrives to an ELB listener which has associated multiple rules, those rules are going to be evaluated by the ELB in a sequential order, following the priority associated with the rule. Then when a match is determined with a specific rule, the target group that is associated with that rule is going to be selected. If none of the rules are going to be matched, there is always defined a default rule, which is going to handle the default case. Rules have conditions associated. Those conditions are actually the ones technically what the ELB is going to evaluate. And those conditions can be based on a great variety of different parameters included in the client request. This can be the path included in the request, the HTTP method. More in general, any type of HTTP header included cookies, query parameters, and also the IP address of the client that used by the client to send the request to the ELB. Now, this rich set of options give ELB great flexibility. And indeed, ELB has been designed to simplify architectures, and it is intended to load balance traffic directly to the targets behind, regardless of the specific technology used in those applications behind the load balancer. One way to simplify those architectures is when, for example, customers have multiple ELBs configured in their account to serve traffic to multiple domains. When they have this situation, they can consider to aggregate those multiple load balancers into a single ELB. And this can be done leveraging host header-based rules. In fact, in the host header, in the client request, it will be contained the domain that the client wants to access. If customers are offloading the TLS to the load balancer, they can configure multiple certificates on the same listener. And then the ELB will be able to present the right certificate to the right request thanks to the support of the server name indication. The SNI is an info that is included in the client request, more specifically in the TLS handshake. And again, in this information, it is included the host name that the client is trying to access. So checking this information, the ELB will present the right certificate to the client, allowing customer to use a single load balancer to serve traffic to multiple domains, also when the HTTPS is needed. This has the benefit of less operational overhead, because they will need to manage only one load balancer in this case, and also in terms of cost optimization. However, when they performing this decision, they should also be aware, be careful of the blast radius. An impact targeting, for example, this ELB will have an impact also on all the domains that it's serving. So it's always a balanced decision between the blast radius and the benefit that they can get with this type of architecture. The second type of best practice I would like to share is regarding the order of the rules on the listeners. So customers in general terms should always prioritize the most utilized rules. This because will enable the ELB to minimize the number of evaluations that is performing on each single request received on the listener. This will have the benefit that, as I said, it will minimize the number of those evaluations, and even if it's true that the ELB is able to scale its capacity based on also on the number of evaluations, it is also true that the evaluation have a computational cost. So for customers that would like to minimize as much as possible the latency added by those evaluations, they should consider to prioritize the rules that are expected to be the most utilized. Last best practice I'd like to share is regarding specifically for internet-facing load balancer. So when customer expose a load balancer to the internet, they cannot really predict what type of request those load balancer is going to receive. Together with some legitimate request, the load balancer is going to receive also a certain amount of random requests from bots, intruders on the internet. So it is a good idea to handle the redirect and reject of those random requests through a default rule. In this way, the ELB will have the responsibility to produce an answer to those random requests without forwarding the request to the target behind. And if we imagine in a specific moment that the ELB is going to receive a very large number of those random requests, the targets behind the ELB will be protected by the ELB scaling system, which will scale up and will absorb this increased amount of traffic. Last mention for the request routing is regarding the weighted target group feature. With this feature, customer can associate multiple target groups behind the same listener rule. And then they can associate a percentage of traffic that they would like to steer to one target group rather than another. This is very helpful in blue-green deployments. In fact, when customers want to roll out a new version of application, they could leverage the weighted target group feature. And in this way, they could test their new version of the application with some real client request. Then if they want, they can also turn on the stickiness at target group level. And in this example, it means that a single client will be routed consistently to the same target group, meaning the same version of the application. Now let's move to the last stage, the target selection within the target group. We will see that each ELB product has associated its own routing algorithm, and for this reason, I'm going to discuss each one of them separately, starting with the network load balancer. NLB is the AWS managed service for layer 4 load balancing, and as a layer 4 load balancer is able to perform the target selection also based on a combination of information at layer 3 and layer 4. When NLB is used with TCP listeners, the target selection is performed when a new connection is established. When this traffic arrives to the network load balancer, a 6-tuple is going to be extracted from the TCP and IP header. This 6-tuple will be the input parameter of a flow hash algorithm, which is the routing algorithm used by the network load balancer to select a target behind and then to forward traffic to it. When performing this selection, the network load balancer will track the association between the 6-tuple and the selected target in a distributed database. We will see in a moment why this is important. Before doing that, I would like to mention something regarding the return of the traffic that is generated by the targets and is sent to the client. Also, this type of traffic will travel through the network load balancer. In fact, when a new connection is established, a target is selected by NLB, traffic is forwarded to that target. Then, thanks to the connection tracking system that is implemented in the AWS Hyperplane, which is, as John shared before, the underlying technology that allows the NLB to manipulate traffic and send traffic back and forth from a client to a target. So thanks to the hyperplane and its integration with the EC2 software-defined network, the return of the traffic is forced to go again back to the network load balancer. And this is not so obvious, specifically when the client IP preservation feature is enabled on a network load balancer. In fact, in this case, the destination IP of the traffic sent from a target to a client will include the real client IP that opened the connection. And this IP is not really an IP assigned to the network load balancer. So for this reason, there is the need of this special type of tracking system, which is implemented in the EC2 software-defined network, will force the traffic to enter back the network load balancer, which is going to rewrite the source IP of the traffic with its own IP, and then send the traffic back to the client. I mentioned the importance of the distributed database. It is important for multiple reasons. The first one is because it allows the network load balancer to avoid recalculating the flow hash algorithm each time that is receiving traffic for an existing connection. In fact, when data arrives for an existing connection, the NLB is going to search inside the distributed database the association between the 6 tuple identifying this TCP connection and a target selected. If it finds a record, it's going to select the same target that initially was selected. So it means that the NLB is going to perform the target selection only once when the connection is established, and then is going to consistently route traffic to the same target that initially was selected, as long as the traffic is exchanged inside the same TCP connection. The second reason, it's something that John already mentioned before, is because maintaining the connection state externally from the physical host in the hyperplane manipulating the traffic, it allows the NLB to replace one of those physical hosts, for example, for a scaling activity, without having an impact on the customer traffic. Every open connection has associated an idle timeout, which by default is set to 350 seconds. When a connection is idle for more than this timeout, the NLB is going to remove the record from its distributed database for that connection, meaning that when traffic arrives for the same connection, the NLB won't be able to find the record in the distributed database, and then it's going to reply with a TCP reset to the client. Since we released NLB, a very popular request from our customers was the ability to customize that idle timeout. And recently, we released this new feature for TCP listeners. Now customers can submit a value, decide a value that goes from 60 seconds to 6,000 for the idle timeout. If you want to know more about this feature, feel free to follow the QR code in this slide. Going to pause for a moment. Okay, when NLB is used with UDP listeners, the same flow hash algorithm is used for the target selection. Here, however, a 5-tuple is used to calculate the flow hash. Protocol, source and destination IP, source and destination port. Here, the missing parameter compared to the TCP listener is the sequence number. And this because we know that UDP has no concept of connections or sequence number. However, NLB is applying a concept of UDP flows, meaning that when traffic arrives for a new UDP flow, the network load balancer is going to select a target, forward traffic to it. Then if that target is going to reply within 30 seconds, the NLB is going to track the association between the 5-tuple identifying this UDP flow and the selected target, again in the distributed database, meaning that also for UDP traffic, the NLB is going to select once the target behind and then consistently route traffic belonging to the same UDP flow to the same target behind. This is an important concept because we see sometimes customers configuring their client to use the same source port for multiple UDP flows. And when this happens, all this traffic will arrive to the network load balancer containing the same 5 tuple, meaning that NLB is going to select just one target to handle all this traffic. So it is important that clients are configured to diversify the source port used for multiple UDP flows, and this will enable the NLB to distribute evenly the traffic across all the healthy targets in the target group. Now let's change product. Let's talk about gateway load balancer. With gateway load balancer, when it's used with TCP traffic, the same flow hash algorithm is used to select a target, and the same 6 tuple is used to calculate the flow hash. Here, however, the association between the TCP connection and the target, it is extended also to the return of the traffic, the one generated from a server to the client. In fact, gateway load balancer, it is a resource that sits in between a client as a server. Both directions of the traffic are entering the gateway load balancer listener. So it is important that the gateway load balancer is going to make a consistent decision regarding the target selected. And this because behind a gateway load balancer, usually it is configured a firewall appliance, which is going to enforce stateful rules on the traffic. So gateway load balancer, for this reason, provides natively this type of stickiness between the TCP connection and the target selected for each direction of the traffic. When gateway load balancer is used with non-TCP traffic, just a 3 tuple is used to calculate the flow hash, source and destination IP, and protocol. Now let's move finally to application load balancer, starting with clarifying when the target selection is performed by the ELB. ELB is capable to perform the target selection for each single HTTP request that it receives. And this is true also when a single client is reusing the same TCP connection to send multiple HTTP requests. Those HTTP requests will be individually balanced across all the available and healthy targets. Then when ELB is going to open a connection with a target behind, we'll try to keep that connection open. This allows the ELB to have a sort of pool of connections that are always ready to be used, and it will avoid the ELB to reopen a TCP connection each time that it wants to distribute an HTTP request to a target behind. Now, if we take this example and we use a network load balancer, as in the left of this slide, for what we shared so far, the NLB will route all those HTTP requests to the same target behind. And this because, as said many times, ELB is capable to route HTTP requests, NLB routes connections. What I shared regarding the ability to select a target for each HTTP request is true as long as session stickiness is not enabled on the ELB. The stickiness is the functionality of a load balancer to repeatedly route traffic belonging to the same client session to the same target behind. This means that when a new request arrives to an ELB with stickiness enabled, if this request is for a new session, then the ELB is going to perform the target selection. If the request it is for an existing session, meaning it will include an AWS ELB cookie, the ELB will look inside this cookie, will see the target that initially was selected, and then instead of applying the target selection following the routing algorithm, it's going to use the target included in the cookie. Meaning that in case there are few clients sending the majority of the requests to the load balancer using existing client session, the resulting distribution will look something like this. Here it's an extreme case where I had just 2 client sessions were sending the majority of the requests. However, it's true to say that stickiness is produces inherently unbalanced distribution by the ELB. So customers should really use it carefully and use it only when they really need it. If it's possible, remove this dependency with the session stickiness. Now let's finally talk about the routing algorithm available on the ELB. There are 3. And this routing algorithm, it is an attribute associated with the target group. If customers don't configure a specific routing algorithm, then the default choice is round robin. With round robin, ELB nodes are maintaining a list of healthy targets that can receive traffic, and then when selecting one target, is going to select sequentially a target inside this list. ELB is the less sophisticated of the routing algorithm options available for ELB. However, it is able to produce very well-balanced distributions in terms of number of requests per targets. And it is indicated in use cases where requests are similar in terms of complexity. They take approximately the same amount of time to be served, or when targets have similar capability in the target group. However, ELB, when using round robin, is not going to perform any type of special logic when performing the target selection. For example, regarding how much busy is a specific target in the target group. This concept is implemented in the list outstanding request, which is the second option for the routing algorithm. With list outstanding request, the ELB nodes are going to maintain a table, including for each target the number of in-flight requests that is handling that target. For in-flight request, I mean a request that has been forwarded to a target behind, but for which the target still didn't produce an answer. So the ELB with this routing algorithm is going to select the target which is handling in that specific moment the least amount of in-flight requests. And doing so, it is able to prioritize those targets that are less busy in a specific moment. In terms of traffic distribution, this means that the list outstanding request it's a very good choice when customers have instances of different easy-to-size in the target group. In that case, the list outstanding request will be able to prioritize those targets with more capability. More capability means also more that targets are able to process requests faster. So it is expected that in each specific moment, that target with more capability is also handling the least amount of outstanding requests. So list outstanding requests will prioritize those targets as it's visible in this graph, where it is showed the number of requests received for each of my 4 targets in the target group. In terms of benefit of this routing algorithm, there is, of course, for sure, an increased availability of a service, specifically in the case where, as I said before, targets are configured of different easy-to-size. Here, I'm comparing a load test using round robin and list outstanding request. With round robin, it was easier for me to overwhelm those targets that had the least amount of capacity. So those targets were producing 5x6 error, 5x6 error that I couldn't see doing the same load test with list outstanding request. And the reason is because my ELB was preferring to route requests to targets that were more capable to process those requests. Last option for the routing algorithm is weighted random. With weighted random, ELB nodes are going to select a target randomly from the target group. Then customers using weighted random have the possibility to enable the anomaly mitigation feature, which is a feature that relies on the anomaly detection system. The anomaly detection system is a capability always turned on ELB, regardless of the specific routing algorithm used. The ELB nodes are going to constantly monitor the target responses returned by the targets. And then they are going to monitor also some CloudWatch metrics showing TCP and HTTP errors. The purpose of this monitoring is to identify targets that are starting to return errors. When this is true, the ELB is going to mark those targets as anomalous. This will be visible from the AWS console and also from the anomaly host count CloudWatch metric. Looking at these 2 sources of information, customer can decide to turn on the anomaly mitigation system. The anomaly mitigation system will allow the ELB to take actions upon those findings. In fact, when a target will be marked as anomalous, the ELB will quickly steer traffic away from the anomalous target, preferring in the target selection the other targets that are considered healthy. However, still will forward part of the traffic to the anomalous targets, and this is done in order to probe the health of those targets. In case, in fact, the anomalous target will start to return successful answers, then the ELB will gradually, incrementally increase the traffic to the anomalous targets until it gets the full share. Now, the anomaly mitigation capability shouldn't be seen as a replacement of the health check system. The health check system still applies and exists. Its main functionality is to mark a target as unhealthy and then stop sending traffic to it. However, it takes time, this process. In the moment from when the targets start to return errors to the moment in which the target is marked as unhealthy, then the anomaly mitigation feature can help the ELB to react faster to this type of events. This type of concept, it is clearer showing the, again, a load test I performed comparing round robin and weighted random. Here, I put one target on purpose out of service, so I stopped a service on a specific target. And while with round robin, requests were routed normally to that target, that was still considered healthy and not considered unhealthy by the health check system. So that target was returning 5x6 error. Those errors were reduced by the use of weighted random because the ELB was able to quickly steer here the traffic to the other healthy targets in the target group. Then, as soon as I essentially restarted the service and the target, you can see how the ELB is gradually increasing the traffic again to the anomalous target. And this is done for an increased availability of the service. In fact, the number of 5x6 errors were reduced. John went in greater detail about weighted random during the last year's session, so feel free to follow this QR code here to watch last year's session from John. This is my last slide. So during this session, we shared several best practices. I encourage you to follow the QR code in these slides so you will access the AWS ELB best practices page on GitHub, where you will find some of the best practices discussed today, together with an extended version of best practices categorized following the pillars of the well-architected framework. And with this, I'll pass the ball again to John, which is going to talk about an exciting feature that we recently released.
Thanks, Enrico. Who has ever had their ELB pre-warmed? Some? Okay, good, good, good. So we just launched this feature, a week ago? It's brand new. We call it LCU capacity reservation, load balancer capacity unit reservation. And before we get into the details of what it does, let's talk about what we all should know about ELB scaling. So ELBs will organically scale no matter what to the detected level of traffic. So if you have a big workload and you're transferring it or you're growing, usually you don't need any of this. It's because we over-provision capacity when we're provisioning it. It's because we have redundant zones where we make sure that we have enough capacity to fail one of those at any time without needing to scale. When we're triggering scaling, we do so very aggressively, so minimum thresholds, try to scale quickly, and then we scale down very cautiously. So we'll gate scaling down to make sure that if you have a typical workload, we are not going to be impacted by scale up, scale down all the time. And then we scale on virtually every dimension of traffic. So if your load balancer receives it, we probably scale on it by its bandwidth, CPU, connection count, you name it. And again, our thresholds are very low, so CPU, 35% is kind of our average. The reason for that is we want to drive over scaling. I did go into this a little bit deeper last year, just to kind of talk about the things we do for scaling. This applies to both application and network load balancer. And With the capacity reservation, you could use it for both application and network load balancer today, and it'll come for a gateway load balancer in the future. This doesn't change your ELB's ability to scale up. It only limits the scaling down, and you can think of it as you're raising a floor of capacity. So if you don't have anything set, there's no floor, and we'll cautiously scale down to almost 0. And if you start to send traffic, then we'll try to aggressively scale up. This doesn't limit further scaling, key point that I'll make many, many times. It usually takes a few minutes, and the API is instant. So when you make the API call, we start configuring the capacity immediately, and then there's a describe you can loop on and say, are we done with the provisioning the capacity? It's available for application and network. I did mention that. So when do we expect folks to use this? Like, what are the use cases that you have that people can, or that you can do to make sure that your events or different things go smoothly? So traffic migration is a big one. We have customers who move from one load balancer to another, or from a different product to a load balancer. And if you have the information in AWS and you have metrics you can go look at, this is the simplest, especially ELB to ELB, because of some of the metrics we've launched. It's also useful for planned events, so if you have a big sale coming or something where you know that you're going to have a surge of traffic to your site at a specific time, it's great to say, we'll go set this an hour or two before the event, let it scale up, make sure everything is good, run the event. And then Mondays, because Mondays, right? We all love Mondays. The Monday case here is based on the fact that we'll scale in 12-hour increments. So if you send traffic to a load balancer and it scales up, we won't scale in, and this is for ALB, since NLB we're a little more dynamic, but on ALB we won't scale in less than 12-hour increments. So if you have a surge of traffic and then you take all the traffic away, it'll be at least 12 hours for each tier of scaling that you've had. And that could be as many as dozens and dozens. It could take days to weeks. But there are people who have two periods or more over the weekend where their traffic is low enough that they'll actually scale down. And then if you have something like a simple example would be a market that opens, and it opens at the same time every day, and all your clients show up at your site to use your products, and it aligns with the market, then you may have scaled down enough from the Friday market close, and you may benefit from using this feature. Intermittent spiky traffic, this one's a little tricky. We'll talk about it a little bit, but if you have a case like this, it's probably good to reach out to AWS support and get some feedback on your use case to see how it works. Because this feature is essentially allocating whatever capacity you tell us all the time. And if you have intermittent spiky traffic, you may want to do other strategies like sharding, which I talked about last year a little bit deeper. On the ALB, so we organically scale up and then out. That means, as you all probably know, we're provisioning EC2 instances, single tenant instances. So when you launch an ELB, we create instances for it. Those instances get IPs. Those IPs go in DNS. Route 53 health checks them and returns them if they're healthy, which is why we say Route 53 or DNS will have healthy and adequately scaled nodes. When we're doing this scaling, we're also graceful about any previous nodes. So if we pull a node out of DNS, we don't shut it down until it has 0 connections for 5 minutes, and will last days and days. If clients don't update their DNS, they'll still be talking potentially to nodes that are out of DNS until they finally completely drain. NLB is slightly different for how it's scaling. So organic scaling on NLB is zonal, meaning one zone's capacity or utilization doesn't drive scaling in the other zones. So if you have an NLB in 3 zones and one of them is getting a lot more traffic than the others, it could organically scale to a much larger size than the others. Now, when you set the LCU reservation on your NLB, we actually divide it into all of the zones. And so this goes back to don't put a zone on your NLB that you're not actually using. And with this feature, we are just looking for what you're provisioning and providing as much capacity as we can, but we're going to spread it to all the zones. When you're planning for your event, so the metric we launched on ALB is called peak LCUs. Anyone see it pop up in the console and say, what is that, and open a case to support? Or, okay. A few people did that. So peak LCUs is the metric that your ALB is saying, this is how many LCUs I think we need for this workload. And the I in this case is actually the ELB scaling system. So our scaling systems are looking at all of those dimensions of traffic and trying to map it to essentially an LCU capacity. The 1 minute sum relates to the 1 hour bill. So if you use 1,000 LCUs in an hour, your 1 minute sum will probably look somewhere around 1,000. If you don't know how much to use or you're moving into AWS, a load test is the preferred way to see. So do a load test to the capacity you think you need or some fraction of it, and then multiply it to the full value based on take the peak LCU and multiply it to the full value. You can also get this from the 1 hour metrics. So 1 minute metrics we only keep for a couple weeks. 1 hour metrics we keep for over a year and a half. The 1 hour metrics are a combination of the 1 minute metrics. And what that means is you can take the maximum of the 1 hour metric and rely on that being the P100 or the maximum of a single node's view for that minute or for that hour. And you can take that and multiply it by the sample count. I know this is tricky math. We have it on our demo site to kind of go through all of this if you're confused, but it is confusing. But so you multiply by the sample count. So you've got the maximum and the sample count. Sample count is how many nodes there are, and the maximum is the most expensive of one of those. And with that, you can go back a year and a half and see we had our same sale. It's our annual sale this year. We can go back and look. The console is also updated to have the same math. So if you look at the console, you'll see these values from the 1 hour metric, even if you're looking at the current time period. So let's look at some what happens when you make the reservation. So you basically will determine how much capacity you want. You tell the API that you want it, we provision it, and then confirm everything is good, you're ready for your event. Once you have the event, or once the traffic hits what you think is the peak of the event, it is safe to remove the provisioning, because when you remove the provisioning, we actually look at the actual utilization for the past 42 hours, pick the highest point, and scale to that. And then we go back to that organic scaling where we're going to cautiously scale down in no less than 12-hour periods on ALB. NLB, it's much faster, but it's also much faster to scale up because we have the capacity sitting there. We can just move it between the hyperplane E and I's. So let's look at some examples of traffic. And apologies for the graph. It's not the best one I've ever made. The green is representing the capacity the ELB is using, and this purple is showing our sinusoidal pattern, which we commonly see with like daily cyclical workloads. So you can think of these as the peak is a day, and then a night, and then a day and a night. And if you're growing, this could be on a faster rate also because we're doubling every 5 minutes. But as you grow organically, we're provisioning a lot of extra capacity as we trigger. So if we trigger on 35%, we're going to have a bunch of capacity sitting there that is ready in case the capacity or the traffic keeps growing. So this is just organic scaling. There's no problems here. It's all well scaled. We see this all the time. This is kind of the normal case for provisioning. The other normal case we see is the sinusoidal pattern where because of the 12-hour delay in scaling, we usually won't scale down between day and the next day. So if your traffic ends late in the day, starts early the next day, you're probably going to be at the same scale you were the day before. If you scale down, say, one level, you won't run into the Monday problem because we're only going to scale down one level, and each level can support the one above it. So the capacity we provision is enough to include a rapid scale up, and then we'll come back and add capacity because we want to maintain redundancy. So the scaling action itself can be thought of more as a backfilling of capacity to plan for future growth or failure. So let's look at our first bad case. Under scaling, so in this case, the traffic is migrating from somewhere to an ALB or an NLB, and we can see that spike went over. We detected the scaling when the spike crosses 35, 45% of the current capacity, but it takes us a few minutes to provision. Because of that, the provisioning might be too late to support the actual spike that your traffic is generating. And for that, we have this new feature, LCU capacity reservation, where you could call it an hour or minutes before, make sure that you're provisioned, and then when the traffic arrives, you can remove it as soon as you hit the peak. And then you'll quickly transition. You have a very fine line where you've got a period of traffic where you know it's coming and you've reserved, and then you remove the reservation. So it's similar for an event, except usually with an event, the traffic scales back down. You do the same thing here. You provision in advance. You start your event. You can remove it afterwards because we won't scale down too quickly. So this is our Monday example. You can see that we had a couple scale downs over the weekend. And then when Monday came, we didn't have enough capacity. And so we scaled, but there were minutes there where we weren't caught up yet. So provisioning an hour before the start of the market is a great way to be ahead of this. And if you looked at this load balancer, the numbers you would see would be here for your LCU metrics. So you would see peak LCU would be one of these, and you could plug that in at this time before your start, and you would actually get the same capacity. Because when you tell us to provision this, we still pad it with all of this extra capacity, just so we're ready in case you need to scale further. So let's recap. This new feature lets you raise the minimum capacity of your load balancer for your application or network load balancer. It starts provisioning immediately. It usually takes a few minutes, and it doesn't block further scaling. So check it out today. It's available for ALBs and NLBs. We will be available in the hall for questions. I know we went to time, but thank you all for joining us.